Hey everyone, today we're talking about the unit circle, so you should be on page 5 in your Unit 2 notes packet. It should look just like this. I'm going to try to go through the notes as quickly as possible to keep the video from being too long, but you should definitely feel free to stop it or pause it along the way as we go, as you need to catch up with all the notes. There's a lot. So this is what we call the unit circle. It is a circle graphed on a coordinate plane, and it is called the unit circle specifically because the radius of this circle is 1. It's exactly 1. So the distance from the center of the circle to any point on the circle is 1. So what that means is that this point right here, if it's graphed on the unit circle, the center is at the origin, then this point is at 1, 0. It means that this point up here is at 0, 1. This point would be at -1, 0. And this point would be at 0, -1. Okay. So we use the unit circle to help us as a reference for commonly used trig angles. So as we go around the circle, we've talked about this a lot. We always start on the positive x-axis. So this would be 0 degrees or 0 radians. But if we go all the way around the circle, it's also 360 degrees and 2 pi radians. So these are what we call, as we said, coterminal angles. This angle starts and ends at the same spot, whether it's a 0-degree angle, a 0 radian angle, or a 360 or 2 pi radian angle. Okay. This would be 90 degrees or pi over 2 radians. This would be, of course, 180 degrees. Ooh, that's not what I wanted. We'll get to that later, why that's there. Or pi radians. And of course, 3 pi over 2 radians or 270 degrees. So we've talked about that. Those are the most common angles, but we have other commonly used angles within the unit circle that we're going to talk about. This is a 30-degree angle, a 45-degree angle, and a 60-degree angle. If we start in standard position and we rotate further, we have a 120-degree angle, a 135-degree angle, and a 150-degree angle. If we open up even further, we go to 210 degrees, 225 degrees, and 240 degrees. Here we have 270, as we talked about, but also 300 degrees, 315 degrees, and 330 degrees. So you should be filling in all of your degree measurements as we go around. If we were to calculate our conversion from degrees to radians, we could also see that this would be pi over 6 radians, pi over 4 radians, pi over 3 radians, 2 pi over 3 radians, 3 pi over 4 radians, 5 pi over 6, 7 pi over 6, 5 pi over 4, 4 pi over 3, 3 pi over 2, which we did already, 5 pi over 3, 7 pi over 4, and 11 pi over 6 radians. So our unit circle is filled in for all of our degree measurements and for our radians. So we're going to use our unit circle for any of these angle measurements that we need to find trig ratios for. So if you recall, these angles we talked a lot about in geometry with right triangles. They made what we called special right triangles. One of them was called a 30-60-90 right triangle, and the other one was a 45-45-90 or an isosceles right triangle. We talked about those specifically because they had always the same ratio of side lengths. So the side across from the 30-degree angle, or the short side, was always half the measurement of the hypotenuse of a triangle. So if we remember that an angle in standard position always starts on the positive x-axis, and we create a 30-degree angle here, we could create a right triangle by dropping a line straight down. So we have a right triangle where the radius I'm sorry, where the hypotenuse of our right triangle is the radius of our unit circle. So that must be a length of 1 because we said all the radii in a unit circle are 1. And this is the angle across, I'm sorry, the side across from the 30-degree angle. So this is always half the length of the hypotenuse in a 30, 60, 90 right triangle, or the hypotenuse is always twice as long. So if the hypotenuse in this triangle is 1, then this side length must be 1/2. Why that's important is because it will give us the coordinate, the y coordinate of this point. So this point is exactly as tall as this right triangle. So the y coordinate of this point is going to be the height of that triangle. Well, the height of the triangle is 1/2 because it's half the length of our hypotenuse. Okay. The ratio of the side that was across from the 60-degree angle, this is our 90-degree angle here, was always the short side times the square root of 3. Or in other words, the square root of 3 over 2 in this case, because our short side was 1/2. And this horizontal distance is the x coordinate of this point. It is how far we are horizontally away from our origin. So this coordinate is at the square root of 3 over 2, comma 1/2. In a 45, 45, 90 triangle, and I'm just going to show you over here for kind of clarity's sake, just to spread it out, or an isosceles right triangle, we had a right angle and two 45-degree angles. I'm using the 135 because 135 is the same thing as a 45-degree angle, just on the opposite side of the unit circle. But this was always in the ratio of 1 to 1, meaning these two sides were always exactly the same. And the hypotenuse was always the length of the sides times the square root of 2. So therefore, if I wanted to find the x and y coordinate here, it would be 1 over the square root of 2, because if this side length is 1, then this has to be 1 divided by the square root of 2. We don't like to have radicals in our denominator, so we rationalize it, and it would be the square root of 2 over 2. And we can talk about that more in class, but just know that these coordinates are at the square root of 2 over 2 because this makes an isosceles right triangle. Okay, and if you don't remember, here's a quick graphic of our special right triangles. So these are always the same length because it's isosceles, and this is always the square root of 2 times that length. So if this side is 1, then this has to be 1 divided by the square root of 2. And then this was our 30, 60, 90. So if you needed to get a quick refresher on that, that's where these points are coming from. So anyway, this happens to be negative because on a coordinate plane in quadrant 2, all of our x coordinates are negative. So it's referring to the direction that we're going because we went to the left. Our x coordinates are all negative here. But on the right side, everything's positive. So we have the square root of 2 over 2 for both our x and our y coordinate here. And that's going to match also for all of our matching angles in quadrant 3 and quadrant 4. So the 225-degree angle, we could make a 45, 45, 90 triangle in quadrant 3. Again, everything's negative in quadrant 3, so both of the coordinates are negative there. And in quadrant 4, the x's are positive, but the y's are negative. So hopefully that gives you some idea of where these coordinates are coming from. So for all of our other angles, there are going to be variations of the square root of 3 over 2 times 1/2 because we're making 30, 60, 90 triangles again, except this time this is a tall triangle, a tall 30, 60, 90. So the tall side, or the y coordinate, is going to be the square root of 3 over 2, and the short side is the horizontal coordinate, or the x coordinate. So that's going to be 1/2. And then this point over here matches this point, except we have a negative x value. Still, the y is positive because we're above the x-axis. This point matches this point over here, but again with a negative x coordinate. And then our points in quadrants 3 and 4 are going to match these. This point matches this one, except our y-coordinate's negative. We talked about this point already. This point is going to mimic this point down here. Again, with the y is negative. This point is going to match this one. It's in the same position on the opposite side. So the x's are positive, but the y's are negative in quadrant 4. And then this point 330 kind of mimics this point over here. So we have the square root of 3 over 2 and then negative 1/2. So there you have it. We filled in our entire unit circle. In functions trig, or if you move on in math, this might be something that you have to memorize. This year you will not have to memorize it. You will get to use a unit circle on quizzes and tests, but you should definitely be familiar with how to use it. Okay, so remember that in a unit circle, the radius is always 1. So if we think back to geometry, we talked about sine, cosine, and tangent, and we used those in right triangles to solve for missing pieces of our missing information from our triangle. The sine ratio was always the opposite side over the hypotenuse. The cosine ratio was always the adjacent side over the hypotenuse, and tangent was always opposite over adjacent. We used the word SOHCAHTOA to help us remember that. So in a unit circle specifically, point that out, in a unit circle specifically, the sine coordinate, the sine of our angle, is always the y-coordinate over the hypotenuse. Well, the hypotenuse is always 1, so the y-coordinate divided by 1 doesn't change, so we can just say that the sine value is always equal to the y-coordinate on our unit circle. Cosine is always the adjacent side over the hypotenuse. Well, the adjacent side to this angle, or any of these angles that we form our right triangles with, is always going to be the horizontal coordinate divided by the hypotenuse. Well, again, the hypotenuse is always 1. So dividing by 1 doesn't change anything, so it's always the horizontal or the x coordinate. Tangent is always the opposite side over the adjacent side. Well, the opposite side is always the vertical coordinate or the y coordinate, and the horizontal side is always, the adjacent side is always the horizontal coordinate or the x. So tangent is always the y coordinate over the x. And then these are 3 new trig ratios that you have not talked about. Cosecant is the reciprocal of sine. So if sine on the unit circle is y, then cosecant is 1 over y, or the reciprocal of it. Secant is the reciprocal of cosine, so 1 over x. And cotangent is the reciprocal of tangent, so it would be x over y. Okay, the last thing we need to talk about are things that are positive and negative. Well, sine and cosecant, because they're reciprocals, are linked together. Wherever sine is positive, cosecant is positive. Wherever cosine is positive, secant is also positive. And wherever tangent is positive, cotangent is positive. So the reciprocals are always linked together. In the unit circle, in quadrant 1, everything's positive. The x's and the y's are always positive. So all of our trig ratios are positive in quadrant 1, and none of them are negative. In quadrant 2, because the x coordinate is negative, that's going to affect cosine and secant, because those are made up of the x coordinates. So sine and cosecant are positive, but cosine and secant are negative, as well as tangent and cotangent, because they're affected by the x's as well. So in quadrant 2, sine and cosecant are positive, but cosine and secant are negative, as well as tangent and cotangent. In quadrant 3, everything's negative, x's and y's. So for sure, sine and cosecant, cosine and secant are negative because they're made up of x's and y's. And tangent and cotangent are positive because they're made up of both x and y. And because they're both negative, the negatives end up canceling out. And finally, in quadrant 4, the x's are positive, but the y's are negative. So again, anything with a y in it is going to be negative. So sine and cosecant are negative, along with tangent and cotangent. And the positive trig functions in quadrant 4 are cosine and secant. Okay. So now we're going to take a look at some problems. Okay, so on the next page, what we're going to have to do is use our unit circle to evaluate the trig functions, meaning to find the value of the trig functions at each of these angle measurements on our unit circle. So we have 6 trig functions: sine, cosine, tangent, cosecant, secant, and tangent. So we learned that if our angle is on the unit circle, we can find sine by finding the y-coordinate at that angle. We can find cosine by finding our x-coordinate at that angle, and we can find tangent by putting the y over the x and simplifying. So you need to have your unit circle next to you. I'm going to put this on dual page display so we can have it up at the same time. It makes it a little bit smaller, but it'll be helpful to be able to see back and forth. Okay, so at pi over 6, here's pi over 6, the y-coordinate is 1/2. So sine of that angle is 1/2. It's as easy as that. It's as easy as finding the coordinate and then, whoops, seeing that sine. Well, I just messed that up. Okay, so like I said, the sine ratio uses the y-coordinate. So all we have to do is find our angle and then find the y-coordinate, and that's the sine of that angle. Cosine is the x-coordinate, so we do the same thing at that angle, and we take the x-coordinate. Tangent is the y over the x, so I put my 1/2 over my square root of 3 over 2. That creates a compound fraction. We can multiply by the reciprocal, which gives us 1 over the square root of 3. We cannot have a radical in our denominator, so we have to rationalize it by multiplying the numerator and denominator by the square root of 3. That gives us the square root of 3 over 3 simplified. Cosecant, secant, and tangent. I'm sorry, that should not say tangent. That should say cotangent, C-O-T. So that's a mistake. Cosecant is the reciprocal of sine, so I just need to flip it. 1/2 becomes 2. Cosine becomes 2 over the square root of 3. Again, I end up with a radical in the denominator, so I rationalize it and simplify. And then cotangent, instead of re-rationalizing and flipping this over, I'm going to take my original unrationalized denominator and flip that, which gives me the square root of 3. So the next angle is 5 pi over 4. So if you just flip around to 5 pi over 4, we're going to be using these coordinates. Sine t is the y-coordinate, cosine t is the x-coordinate, tan t is the ratio of the y over the x. And because they're exactly the same in this point, they're going to simplify to 1 or reduce to 1. And of course, cosecant, secant, and cotangent are all of the reciprocals of these. So I just need to flip that. This has been rationalized. It was negative 1 over the square root of 2. So if I find the reciprocal of that, that becomes negative square root of 2 over 1. Same thing with secant. And then the reciprocal of 1 is 1 still. So again, notice because 5 pi over 4 was an angle that was in quadrant 3, tangent and cotangent were the only trig functions that stayed positive. Everything else was negative. And also we can tell just by the coordinates there. Okay. The next angle is pi. So that's over here. We're going to use the -1 and the 0. The y-coordinate for sine is 0. The x-coordinate's -1. Tangent is y over x. So 0 over -1 gives us 0. Cosecant is the reciprocal of sine. So 1 over 0 is undefined. The reciprocal of cosine, or -1, stays -1. And again, the reciprocal of tangent, which ended up being 0 as well, is going to be undefined. Okay. If you ever have to find an angle that's not on the unit circle, but is coterminal to the unit circle, then you just need to find its coterminal angle by adding or subtracting a complete circle. So in this case, -π/3 plus 6π/3 gives us 5π/3. So we'll use the 5π/3 angle, which is in quadrant 4, to find all of our ratios. And we do that the same way we did before. Sine is the y-coordinate. So here's the y-coordinate at 5π/3. And it's -√3/2. Cosine is 1/2. And tangent is -√3/2 over 1/2, or the y-coordinate over the x-coordinate. So if I simplify that, that gives me -√3. Again, just dividing by a fraction means multiplying by the reciprocal. Finding the reciprocal of sine gives me -2/3, but then I have to rationalize. Finding the reciprocal of cosine is a lot easier. In this case, it's 1/2 to 2. And the reciprocal of tangent would be -1/3, but again, that needs to be rationalized. And there's our final answer. But you'll see we're going to be using a lot of the same fractions here, so it should get easy. Okay, and then finally, in example 2, we're going to see how to do these inside the calculator, which is kind of nice. You won't get to do this very often, so enjoy it. So you're going to get decimals oftentimes that do not terminate. So you're going to round your answer to the thousandths. That's 3 decimal places, unless it's specified otherwise. So on your calculator, if you take a look, let me open this up. Oh, that's not what I wanted to do. Just to make this bigger again. To type in the sine of 2π/3, we need to make sure that we're in either degree mode or radian mode, depending on what they give the angle in. In this case, it's radians. We can tell by the pi's. And the only time it's ever going to be degrees is if you see a degree symbol. So calculators always default to radian mode because, again, they're used by mathematicians, and mathematicians prefer radians. But to double check, just press the Shift and the menu button once you're in the Run menu to get to the setup screen, and you want over here where it says angle to be selected to radians if you're in radians, or of course degrees if you're in degrees. Okay, once you're in the right mode, we have a sine, cosine, and tangent button, so you just have to press sine and then enclose inside parentheses whatever your angle is. So this is 2π/3. And then press execute. Just round to 3 decimal places. It's as easy as that. Okay. And here we have cotangent of 1.5. Again, 1.5 doesn't have pi in it, but it is radians. It is in radians. It's already been multiplied and rounded by pi. We don't have a cotangent button, nor do we have a secant or a cosecant button, but they're the reciprocals of these 3. So when we type it into the calculator, we just need to type it in as 1 over whichever function it's the reciprocal of. So tangent in this case. And then we put in our angle and then press execute and we get our answer. And that's all she wrote. So that's the lesson on unit circle. On the unit circle, you are going to need to complete some classwork. So these are the problems in the practice page that are required, and then of course here are the optional pages, and then please come in next class with any questions that you guys have. See you soon.